Hey everyone, and welcome to another deep dive. Today we're taking a closer look at the fascinating world of liquid behavior,
Yeah,
specifically surface tension and capillary action.
right.
These are forces that work at a microscopic level,
Mm-hmm.
but they have huge impacts on the world around us.
Yeah, definitely. Like they're everywhere.
Ready for some serious aha moments?
Yeah, I think we're gonna have a lot of those today.
Awesome. So what's really cool is that both surface tension and capillary action
Mm-hmm.
kind of come down to the same fundamental forces, right? Like
Exactly.
cohesion and adhesion.
Yeah, those tiny molecular attractions that
Right.
hold everything together.
Okay, I'm intrigued. Let's start with surface tension.
Sure.
I always think of it um,
Mm.
like an invisible skin on the surface of water.
That's a great way to visualize it. It's not a literal skin, of course.
Of course.
But the forces between the molecules at the surface act like one.
Okay.
So you see, liquid molecules are more attracted to each other.
Hmm.
That's cohesion.
Yeah.
Than they are to air,
Okay.
which is adhesion.
So the molecules at the surface get pulled inward.
Exactly.
Interesting.
Creating this tight, elastic-like layer.
So like they're all kind of holding hands,
Yeah.
trying to stay as close together as possible.
Exactly, like a little huddle.
But wait, if they're all pulling inward,
Mhm.
why doesn't the water just like collapse in on itself?
That's an excellent question. It all comes down to balance.
Okay.
So that inward pull from the surface tension
Right.
is countered by the outward push of the liquid's internal pressure.
Oh,
Think of it like a tug of war
okay.
with the surface tension pulling in
Right.
and that internal pressure pushing out.
I see. I see.
Yeah.
Okay, so that makes sense. So then how does this skin explain those perfectly round raindrops we see?
A classic example. So a sphere is nature's most efficient shape when it comes to surface area.
Interesting.
By forming a sphere, a raindrop minimizes the number of molecules
Okay.
that are exposed at the surface,
Right.
which in turn minimizes the energy
Yeah.
needed to maintain that tight surface skin.
It's all about being energy efficient.
It is. It's all about finding the lowest energy state, even for a tiny droplet of water.
So raindrops are basically tiny little energy-saving ninjas.
Exactly.
Oh,
And this principle of minimizing surface area explains a lot of other cool phenomena, too.
Like what?
Think about those little bugs that can walk on water.
You mean water striders?
Yes.
I've always wondered how they do that.
Mm-hmm.
Do they have like some
Yeah.
kind of sticky feet?
It's actually the opposite.
What?
Yeah, so their legs are coated with a waxy substance that repels water.
Huh.
This means the water molecules don't want to stick to their legs at all.
Interesting.
So when a water strider steps on the surface,
Okay.
it doesn't break the surface tension.
Wow.
Instead, it creates these tiny little dents
Mm-hmm.
that the water tries to smooth out,
Okay.
pushing the bug upward.
So if their legs were wet,
Yeah,
the surface tension would actually pull them down.
precisely. It's such a delicate balance, and
Yeah.
it highlights how powerful surface tension can be, even at such a small scale.
This is blowing my mind.
It's wild.
Okay, but how does capillary action fit into all this?
Yeah.
Like, is it basically the same as surface tension?
Okay.
Just different?
That's where things get even more interesting.
Okay.
So while both surface tension and capillary action are driven by those same molecular forces,
Mhm.
they manifest in different ways.
Gotcha.
You can think of surface tension as being all about the surface of the liquid
Okay.
and its tendency to minimize its area.
Like that invisible skin we were talking about.
Exactly.
Always trying to stay as small as possible.
Yep. Now, capillary action is more about the interaction
Mhm.
between a liquid and a solid
Okay.
in a narrow space.
Yeah.
It's the movement of the liquid within that space,
Okay.
and often against the force of gravity.
So it's like surface tension is the engine
Hmm.
and capillary action is the car.
I like that analogy.
Okay, cool.
So surface tension provides the initial force,
Yeah,
and capillary action is how that force manifests itself in a narrow space,
right.
causing the liquid to move in sometimes surprising ways.
Okay, give me an example. Like what kind of surprising ways?
Think about plants.
Okay.
They rely on capillary action to draw water up from their roots to their leaves,
Oh, wow.
even against the force of gravity.
So those massive redwood trees
Yeah.
are basically giant capillary tubes.
In a way, yes.
Wow.
It's the combination of surface tension and the attractive forces between the water and the plant's internal structures
Right.
that allows water to travel upwards, defying gravity.
Okay, now that's just mind-blowing.
It is pretty cool.
So capillary action is like this secret superpower that lets liquids climb walls?
You could say that.
Wow.
It's also at play in things like the absorption of ink in a pen
Oh, yeah.
or the wicking away of sweat by certain fabrics.
So we see both surface tension and capillary action all around us every day without even realizing it.
Exactly.
Wow.
There are these amazing hidden forces that shape so much of our world.
That's incredible. I'm starting to realize that surface tension and capillary action aren't just about
Yeah.
science experiments and
Yeah.
textbook definitions.
Right.
They're all around us,
They are.
constantly shaping the world we live in,
Absolutely.
which is all incredibly cool. But you have to ask,
Yeah.
are surface tension and capillary action always working together?
Mm-hmm.
Or can they ever work against each other?
That's a great question.
Yeah.
And the answer is it depends.
Okay.
Sometimes they work together.
Right.
Sometimes they oppose each other.
Okay.
And sometimes one is more dominant than the other.
I see.
It all comes down to the specific situation and the balance of forces at play.
Can you give me a concrete example?
Absolutely. Let's go back to the example of water in a glass.
Okay.
You'll notice that the water level is slightly higher at the edges, forming a curved surface,
Okay.
called a meniscus.
Oh, yeah. I've always wondered about that. Why does water do that?
That's a great example of the interplay between surface tension and capillary action.
Okay.
The water molecules are attracted to the glass.
Mm.
That's adhesion.
Right.
And this attraction pulls the water upward along the edges.
Okay.
At the same time, surface tension tries to minimize the surface area, pulling the water inward towards the center.
So it's like a tiny tug of war happening right there in the glass.
Exactly. In this case, adhesion is slightly stronger.
Okay.
So the water curves upwards, forming a concave meniscus.
I see.
But if we were to use a liquid like mercury, which doesn't like to stick to glass...
The meniscus would curve downward, right?
Yes.
Because the surface tension would be stronger than the adhesion.
That's exactly right. It's like the mercury is trying to avoid touching the glass as much as possible.
Wow. I never realized how much was going on in a simple glass of water. So we've talked about how temperature affects these forces, but are there any other factors that can influence them?
Absolutely. One of the biggest factors is the presence of other substances.
Okay.
Adding solutes to a liquid can either increase or decrease surface tension.
Interesting.
For example, adding salt to water actually increases surface tension.
Really? Why is that?
Well, salt ions are more strongly attracted to water molecules than water molecules are to each other.
Huh.
So when you add salt,
Okay.
those ions kind of crowd the surface,
Right.
making that invisible skin even tighter.
So it's like adding extra bouncers to the molecular party at the surface.
Exactly. But on the other hand, adding soap or detergent to water will decrease surface tension.
Right.
That's because soap molecules disrupt the cohesive forces between water molecules,
Okay.
making it easier to break that skin
Right.
and allowing the water to spread out and penetrate more easily.
So that's why soap makes water so much better at cleaning things.
Precisely. It's all about manipulating those intermolecular forces to get the desired effect.
That's so cool. Okay, so we've talked about how solids can affect surface tension.
Yeah.
What about capillary action?
Mhm.
Do those same principles apply?
Yes and no.
Okay.
Remember, capillary action is all about the interaction between a liquid and a solid in a narrow space.
Right.
So the type of solid and the size of the space also play a huge role.
Can you give me an example?
Think about a thin drinking straw versus a wide one.
Yeah.
If you dip both straws into water, the water will climb much higher in the thinner straw.
Oh, yeah, I've noticed that. Why does that happen?
It's all about the ratio of surface area to volume.
Okay.
In a narrow tube, the adhesive forces between the water and the walls
Right.
are stronger relative to the volume of water being pulled upward,
Gotcha.
so the water can climb higher before gravity starts to pull it back down.
So the narrower the tube, the stronger the capillary action.
Exactly.
That's fascinating.
And this principle is used in all sorts of applications, from designing medical devices to creating high-tech fabrics that wick away moisture.
This is all incredibly cool. But I'm starting to realize that surface tension and capillary action aren't just about science experiments and textbook definitions.
Right.
They're all around us,
They are.
constantly shaping the world we live in.
Absolutely.
I completely agree. I feel like we could talk about this forever.
Me too.
But I think we've given our listeners a lot to think about.
Yeah, definitely.
Any final thoughts before we wrap up our deep dive?
I feel like we could talk about this forever.
Me too. But I think we've given our listeners a lot to think about.
Yeah, definitely.
Any final thoughts before we wrap up our deep dive?
It really is incredible to think that something as simple as a drop of water can hold so much complexity.
It's like a whole secret world has been revealed right there in front of our eyes.
Exactly. And you're right, we've only just begun to explore the wonders of surface tension and capillary action. There's still so much to discover and learn about these fundamental phenomena.
Well, I don't know about you, but my brain is officially full. I need a glass of water and a moment to process all of this amazing information, and I bet our listeners do too.
I think we all could use a little hydration after that deep dive, but hopefully next time you see a raindrop clinging to a leaf or watch a paper towel soak up a spill, you'll have a newfound appreciation for the invisible forces at work.
I know I will.
It's a reminder that even the most familiar things can be full of surprises when we take the time to look closer and explore the science behind them.
Beautifully said. And on that note, we'll bring you to ponder the wonders of surface tension and capillary action. Thanks for joining us on this deep dive, and we'll catch you next time.
Yeah, I feel like we could talk about this forever.
Me too. But I think we've given our listeners a lot to think about.
Yeah, definitely.
Any final thoughts before we wrap up our deep dive?
It's incredible to think that something as simple as a drop of water
Right.
can hold so much complexity.
It really is. And it's like you said, we've only just begun to explore
Yeah.
the wonders of surface tension and capillary action.
It's true. There's still so much more to discover.
Definitely. And so much to learn about these fundamental phenomena. Well, I don't know about you, but I need a glass of water after that deep dive,
Me too.
just to process all this amazing information.
Yeah, a little hydration is definitely in order.
And I bet our listeners do too.
I think we all could use a little bit after all that science.
Right. Well, on that note, we'll leave you to ponder the wonders of surface tension and capillary action.
Yeah, go out and observe them in the world around you.
Exactly. Thanks for joining us on this deep dive.
It was a pleasure.
And we'll catch you next time for another fascinating exploration.